not exactly German, but more similar. But for example, if you see the lab of Mario, now three professors. Because Mario left and three professors keep there. But in the past, in the beginning, just Mario, but in US or Germany. But now it's three professors. One of computer vision, other of robotics, and a new one that's work with planning and this kind of things.
There are some German universities where there are multiple professors in one, like TUM. They have
because
some.
TUM is
They have some in which they have one lab, but they have like three professors.
in Kitty, no, in household.
Yeah, KIT is more. That's like traditional, so they have one professor.
More Não, eu vou introduzir e vou sentar ali. Just say that I will introduce you and sit there. And
Okay.
The floor is yours. That's all.
Alô.
Keep it short.
Yes,
Don't need
yes.
to say a lot.
No. I will keep it short.
Yeah.
Good morning. Let's start our first plenary talk of the first CROS. So I'd like to thank you everyone to came here for Belo Horizonte to with us to share knowledge about robotics. And now it's a pleasure for us to receive Professor Abhinav. Professor Abhinav is full professor of the University of Freiburg, being the director of the Robot Learning Lab. He is also member of the Computer Science Department in the University of Freiburg and founding of the ALICE unit of Freiburg. ALICE is an artificial intelligence initiative in Europe. He is also chair of the IEEE Robotic and Automation Society Technical Committee on Robot Learning. And he received the PhD on University of Freiburg and the master in the Robotics Institute of Carnegie Mellon. So Abhinav is working with the intersection between robotics, machine learning, and computer vision. He received several awards, but for now, just give the floor to Abhinav. Thank you to come to Brazil, and the word is yours. Thank you.
Thanks a lot, Paulo. All right, thanks a lot for being here, and thanks for inviting me. It's a great pleasure to be here. And today I want to share some thoughts about what I think is one of the next big frontiers in robotics, which I think is open world autonomy, and learning is going to play a very large role in enabling this capability. So I'm a roboticist. I love to build robots. I still like to see robots around me, and I think today is a great time for this. So we have seen many applications where we have more robots than ever in our world. And as you can see, most of our cars are made by robots. Most of our Amazon packages are delivered by robots. And today, even in some hotels, you can have these Savioke robots bring you your room service to you. But if you can see, these environments are still fairly constrained. So there's not much, there's a little bit of dynamic objects, but they don't do anything out of the ordinary here. And in more complex environments like space exploration or medical surgery, we do have robots, but these robots are still teleoperated. And, but we as roboticists always imagined robots to be doing tasks like these, as you see here, be it self-driving cars or our autonomous personal home robot butlers. And we've had these dreams since the 1900s, right? And it's been like 100 years after that, and we still don't have these. So let's see why this is so. And today we still have these same visions as before, since the 1900s, but I would say with a modern twist. And in fact, I think what we expect out of robots has increased. So we no longer just want one robot that does one thing. We want one robot that does a lot of things, from doing your laundry to cleaning your kitchen to maybe putting away the toys of your children. And this is what we see here. So in the video on the bottom, you see a modern twist to this, essentially, so where we collaborated with Toyota here to just dramatize what of the tasks that we see robots do in the future. And I think we all agree that whether it is self-driving cars or personal robot butlers, we are not really remotely close to having this in our daily life. And to understand why, let's quickly look at what has fueled the progress of AI in the recent years. So I think we can all agree that we have seen dramatic progress in the capabilities of AI, be it ChatGPT, Sora, which can generate images, or even music videos with music that we see today. So all of these diffusion models like LLM, VLM, VLAs, and all of these variants, this change has just been remarkable. And I think no one really imagined the capabilities of these models. And if we think about what really made these models so capable, so on one hand, we have these large data sets which have like trillions of tokens, right? Which, especially this text data, is trained from internet-scaled text, like all the text that's available on the internet. And to digest these, we have these transformer models that are like have trillions of parameters to train these with large amounts of data. And this is comparable in robotics to, for example, you have training objectives which are like behavior cloning or imitation learning, where you get a set of demonstrations and you have a set of past states, and you make these models to predict essentially what the future control actions is going to be given the past states of these robots. And of course, this essentially boils down to data models is equal to compute. We get this amazing performance, we can all go home, right? But it turns out that it's not so easy. So what has really worked for vision and language is not really working for robotics as well as we thought that it would. So this is what happens if we do this in the real world. So the key recipe of today's AI, which amounts to a large amounts of data and over-parameterized models, is insufficient for generalizable robot learning. And this is because robot models are essentially designed to interpolate smoothly within the training distribution. And the problem here is that collecting data sets for robotics is really, really hard, right? So we don't have really these internet-scale data for demonstrations, for example. And the second part is that the world is not really what it seems to be like only as we see in the data sets. So our world is constantly evolving. We have unpredictable scenarios that are not really captured. It's rather like impossible to capture in any large data set. And I think this again goes back to Moravec's paradox here, where things that we thought are really difficult for humans, like, for example, playing chess or playing Go, for example, are relatively easy for computers to do. And what's really hard is to be things that we take for granted, like just grabbing a cup and drinking water, or putting groceries into shelves, and so on. And for example, I think it's really funny. We have, some of you might have pets at home, and if you see your pets can really perform these complex maneuvers navigating through a really cluttered environment. And any 10-year-old child can, for example, clean up a dirty kitchen. But today's AI, however, can pass bar exams and do really complicated math, but not really the things that are very, very easy to humans and come for granted. So we keep bumping into this Moravec's paradox again. So this is essentially because a world is extremely complex. So we have a large number of hazards, unusual situations, and harsh conditions that are geographically unique. And it's, I think, really impossible to capture all of this in any data set. And you certainly cannot plan for this during deployment. So sometimes you need to plan for things that are really longer in term, and these things are not predictable while we are developing models for robots or while building these robots. So how do we solve this? So as usual, as roboticists, we like to take inspiration from biology, and whether it is animals or human infants, so these learn surprisingly fast. So on the left, you see a baby elephant here that is learning to use a trunk, and they only take about 8 months to do so, which is less than 2,000 hours that they are actually awake since they are born. And for learning broad, one of the best examples is a human infant. So here you can see a human infant who's actively exploring the world to collect multimodal data. And an infant has a tremendous amount of exploration, physical interaction, and social interaction capabilities. So they autonomously acquire knowledge, become able to predict the results of their actions, results of how the environment changes with these actions, and gradually become able to act effectively in the real world. So what we need for future intelligent robots is to understand how the world works and not just vision and language that we're able to do today. So to achieve these capabilities in robots, today I would like to talk about a few key challenges that I think are important. First would be the agency to learn better representations that effectively generalize in real-world environments. And this relates to latent concepts of objects, how objects relate to one another, the cause and effect, and reliable estimates for example, uncertainty. The second is how to continuously acquire new knowledge and improve the performance over time. You don't want fixed models that you train once, then you deploy it, and that's it. But you want these to continually learn or lifelong learn as the robots are deployed. The third would be essentially how do we enable robots to recognize and adapt to unknown situations, unknown objects, and unknown environments. So if you have robots working in the confined workspaces as we saw in the first slide, this is not really a problem. But if you want the robots to work in the open world, this essentially becomes a critical factor that we need to address. So the last would be how do we enable them to reason over really long horizons? So we can leverage, for example, common sense priors from things like large language models, which we are doing right now to enable this capability. So let's look at each of them throughout these talks. So let's start with semantics, because semantics, I think, are some of the very basic fundamental thing of perception that we need to understand about the world. So we've done quite a lot of work in these directions since early deep learning times to now. So I think we can predict supervised learning semantics quite well. So at that time, when we started doing this, essentially, we wanted to have accurate boundaries of objects, so on and so forth, that you can see on the left. And then we started to progress to more complicated tasks. For example, on the right that you see here, can we take a monocular camera image as input and predict these top-down semantic or panoptic maps? And what's the benefit is that with robots, you can do planning directly on these top-down maps, and it's very hard to do this if you just want to use a perspective view image. And of course, we want to use this for downstream planning and other tasks. So we want to estimate not only what the semantic class is, but you also want to be able to estimate how reliable are these predictions. So that's what you see on the bottom. Now for LiDARs, where you see uncertainty estimates for each point that you're able to predict these semantics. So this is great, right? We're able to do all of these capabilities with learning, but if we look at how well these models are actually performing over the years. So this is when we started working on this. So actually, this is when we published it, like early around 2019. So we made quite a lot of progress. So this is performance on the very influential Cityscapes benchmark, which is, I think, quite standard to do if you do any kind of semantic scene understanding. But if you look at, since then, we've had like a lot of progress, essentially in deep learning, like transformer models, diffusion, but the performance has not really changed so much since then, right? Even now, today, this is still the same performance on the Cityscapes leaderboard. So this was quite astonishing for us to look that we're not really getting so much further. And this made us essentially rethink how we can fundamentally approach this problem of learning semantics out of the environment. So again, we took inspiration from humans. So humans have this remarkable ability to perceive the world as a whole, regardless of whether objects are occluded or not. So for example, if you see a scene and you block part of the scene, you can still imagine what is this scene going to look like in this blocked part. And this forms really a great step in the cognitive understanding and reasoning for humans. But what we do today for robots is still take sensor data, analyze what you can see in the sensor data, and make predictions based on it. So this is essentially modal, but humans have this amodal ability. So we wanted to enable our robots to do the same. And for this, we created this new task that we call as amodal panoptic segmentation. So what this means is that for each pixel, we want to estimate the semantics, the object ID, regardless of whether it's occluded in the scene or not. So that's what we want to do. So here's a visualization where you see a highly occluded street scenes, but as you can see, you have these amodal masks of these dynamic objects, essentially, also in the occluded area. Since this task itself doesn't exist, we had to create new data sets. So we extended two popular data sets, the Kitty and the BDD 100K data set with annotations. So how did we do this? Lots and lots of master students and PhD student hours. And we annotated these two data sets, and we also wanted to have an initial method to show that this is actually feasible to train in the real world. So we have two methods that we developed over the years. One is a proposal-based method, and another is a proposal-free method. So what's interesting here in the results, the plot that you see here, is that now the green bar essentially shows you the performance, how well you're able to identify instances, all right? So, and the method in the last is our method compared to the previous baselines that we have. And you can see that just incorporating this amodal ability in our segmentation models, the accuracy of the instance segmentation substantially increases. And this comes for free, right? This is not like using more data or anything, same data, but just incorporating this amodal ability in models. So if we look at some qualitative results here, so this is a very crowded street scene, I believe in New York here, when there are lots of cars that are moving around, but you can see that a model also predicts the occluded regions of these objects. So just in a second, you will see lots of people crossing the street, and the model does fairly decent job considering that this is like essentially the very basic first work that tried to do this. So we really want the community to use this, right? So for that, we want to create a larger data set. So we create a data set in simulation because real world, it's very hard to predict the occluded regions. But we can do this in simulation quite well. So we created this very large data set having 1 million annotations for several semantic classes and for several perception tasks that we would like to use for robotics, from semantics to panoptics to optical flow to object tracking, so on and so forth. If you are interested in this, you can take a look at this data set that's called A-Modal Synth Drive. And we already started working on showing the benefits of this A-modal ability for several tasks in robotics. So here you see A-modal optical flow prediction, where you can predict the optical flow field also for occluded regions of objects. And on the right, you see the A-modal tracking ability. So we want to do multi-object tracking with this A-modal flow. And what you see here is this gray bar here. So this shows you by using A-modal optical flow, we're able to improve tracking substantially higher than just using standard optical flow. And these are just some examples that we want to show where we want the community more to use this A-modal representation that we have for robotics. All right, so most of the stuff that we've seen until now is still fairly supervised learning, right? So you have your sensor data, you have what you want your model to predict, and then you train your model to do these learning tasks. But I think in order to truly develop large-scale learning systems, we need to alleviate the models from requiring these large amounts of labeled training data. So if you take any modern LLMs that are typically trained on about 30 trillion tokens, which is essentially all the text data that's available on the internet, this amounts to 10 to the power of 14 bytes. And this would take a human approximately 450,000 years to read, which is not really possible for any human so far, at least. But if we compare this to a human child, let's take a 4-year-old child that has only been awake for about 16,000 hours. A human child has remarkable amount of capability for just being awake for 16,000 hours. And a 17-year-old teenager can essentially drive a car in just 20 minutes of training of how to drive a car. But then if you compare this to what autonomous driving companies have so far, I think Waymo recently reported that they have 22 million miles of data that they use for training. And this is like hundreds of thousands of hours of driving. And we still don't have autonomous cars that can drive as well as humans can do. So the question here is, how can we make these models more efficient in terms of the amount of training data that they require to do these learning tasks? So again, we look at the semantic tasks. So in computer vision, we have this problem that is called weakly supervised or semi-supervised segmentation, right? So with very sparse labels, we want to learn these semantics. But if you look at how well these models perform to fully supervised learning, there's this massive gap. So it's not like only a few points, but really an immense gap, as you can see here in this plot. So what we want to do is use foundation models that we have for vision. So this comes from the vision community. And we want to take very few labels, let's say 10 annotated labels, and you want to train now a segmentation model that uses these foundation model features with 10 annotated labels to achieve really as close as possible with fully supervised learning. So with 10 images versus 3,500-ish images. So for this, we earlier proposed an approach that we called as Spino. So Spino enables few-shot segmentation by exploiting these descriptive features from unsupervised task-agnostic models like DynoV2, for example. So here we have our model, which consists of a DynoV2 backbone, and we have a semantic segmentation head on top of that, and a small instance filtering step for detecting object boundaries. And we have a fusion scheme to combine this. So very little trainable parameters apart from just the dyno itself, which is pre-trained. We don't train it right now. So with this, now we take 10 labeled images, and we learn this task of learning semantics or panoptics. And then we use this trained model to now give us pseudo-labels. These are not actually accurate labels, but pseudo-label predictions with these foundation semantic models. So with this, we get a lot of pseudo-labels from very diverse data, and we're able to then use these pseudo-labels to train any state-of-the-art existing panoptic segmentation model. So that's how this works. And surprisingly, this works quite well. So as you can see in this plot, the right two bars that you see are two of our methods that we proposed here, Spino and the following work, Pastel. And you can see that with 10 labeled images, we are almost achieving good performance as fully supervised learning, which uses 3,000 odd labels. And with now further increasing it to about 100 labels, we are able to achieve comparable performance to fully supervised learning. I think this is really great. That shows the potential that we should not always only do fully labeled supervised learning. And you can also see from the qualitative results that this is quite stable. And considering that here we only use 10 labeled images to learn this. Okay, so we also did this very recently for LiDAR data. So as you saw with images, so these are very recent work that we just put on archive last month. So one in which we employ an approach very similar to Spino, and we do the same for LiDAR points. And what we also did recently on the right, this paper, instead of doing this pseudo-labeling, we use something called adapters, where you have most of the model fixed, but we only train what we call as an adapter, which is a very small network in parallel to give us these LiDAR predictions. So these two methods now enable, again, very few-shot learning with LiDAR data for learning the semantics. All right, so what happens now when you encounter objects that you have never seen before? Let's see an elephant like this on the middle of the road, or let's say a cat on a bag that somebody has forgotten on the sidewalk that you see here on the left. So what would typically happen is that because your model has never seen this during training, it would give us these misclassifications. It would put one of these pixels into the n number of categories that you train your model to do, right? And this is not what we want. We want our models to essentially be able to say what it doesn't know. So you can do this with uncertainty. For example, just take your uncertainty predictions of your model and just do confidence thresholding. And you're able to say how well your network doesn't learn. But this is not as accurate as it could be. So what we want is essentially something like this, where you want an entire object mask telling from the model that it doesn't know this class, that it's never seen before. So for this, again, we tackle this with a task that we call as panoptic out-of-distribution segmentation. So in addition to pixel-wise semantics and instances, if there is an object that it's never seen during training, we want to also let the network segment this as a whole object mask, and to tell us that it doesn't see this object. This is really hard, right? How do you enable the network to actually tell something that it doesn't know? How do you enable the network to tell something that's coming in the future, which it has no idea about while you develop the model? So for this, again, we have a metric. We have data sets, if you want to use this, that we extended Cityscapes and Kitty with these annotations of many out-of-distribution objects. And we also have an approach to do this that's called pods. So the way that we do this very briefly is that we have a contextual model that learns these foundation features from, let's say, some arbitrarily existing backbone. And we have two pairs of symmetric decoders. So it's the same decoders that you see here on the purple and the green, two sets of those. And one of them is trained only on the semantic classes that you care about. And the other set of decoders now are trained to only segment out-of-distribution objects. And how do we train this is we just take random objects from the internet and we paste it into images. We do some post-processing. And then we enable the network to predict what it doesn't know. So and then what you're able to do is you have one stream that predicts what it knows, one stream that predicts maybe something it doesn't know. And we have a loss function that we call as alignment mismatch loss that's able to then align these predictions while training to tell the network what it's always supposed to know and what is something that it probably doesn't know. So again, some qualitative results, as you see here. So this is actual results, not on a data set from our car that we drive in Freiburg. We also put random objects in the street, like things like trash cans and, I don't know, teddy bears and so on, that a model has never seen. Never seen this environment, never seen these objects. And you can see for the first try, this does quite well, and this outperforms basically uncertainty-based confidence thresholding methods. Okay, another thing that robots also need to be aware of is like changing environments, right? A world is not always the same. For example, we might have self-driving cars or self-flying cars in the future. We already have a lot of these bikes that I think are super annoying, that are like everywhere in the street in some of these countries. And companies basically have spent millions of dollars creating annotated data sets. Now, if we have a new object that's appearing later in the future, they have to spend, again, all the money to annotate the data because these new objects are not there, right? So this is really not practical if you think about it in the future. So there is class incremental learning that we can do this with vision-based techniques. But typical class incremental learning assumes that the objects that you want to segment are part of the background, but you don't essentially, you ignore it, but you don't take it into consideration while learning. So if you deploy this on our self-driving car data, it turns out it works horribly. So you have performance that are far less than 50, so it's essentially unusable at this point. So to address this, we introduced very recently a work that we called as topics. So topics essentially enforces that features conform to taxonomic tree structures in the hyperbolic space. So rather than Euclidean space, we learned that the hyperbolic space is better for maintaining these taxonomy tree structures that you have with different semantic classes. So as new classes appear over time, such as now we have lane markings that was not there before, so they are appended to fitting positions in the taxonomy tree to maintain essentially their semantic relationship. As a result, the overall class distribution that we get is quite rigid, but here our supervision now provides the plasticity for old classes as the ancestors are also updated during training. So apart from these explicit taxonomy relations, we also leverage implicit relations between the classes to avoid what we call as catastrophic forgetting that happens in incremental learning. So again, we evaluate this on cityscapes and mapillary vistas. As you see, as the model is running, new objects appear over time that the model has no idea about. So these are predictions essentially on the cityscapes data set. All right, so let's move on from semantics to something essentially, which is again essential for robotics, which is SLAM here. So here we're tackling visual SLAM, and robots operating in the open world encounter a wide variety of different environments. For example, self-driving cars need to go from city to city, and so these cities' environments can be substantially different from one another. And in recent years, we made tremendous progress, I think, on learning-based visual SLAM systems. But the caveat is that learning-based methods do not generalize well when you have large amount of domain gap between your training data and your testing data. So we wanted to tackle this problem, and we essentially formulated a task that we call as continual SLAM. So we have this concept of lifelong SLAM in SLAM since decades, right? But essentially, lifelong SLAM only tackles changes across time in an environment, in one environment that you have. And in deep learning, we have this concept of domain adaptation, where you can train this domain adaptation model to adapt one model from one domain to the other, but you need to do this again and again as we go from one environment. So here we wanted to have this bidirectional transfer from many environments, not only one direction, but both directions. So that's what we call as continual SLAM. And one of the methods that we propose to do this, that we call as CL SLAM here, contains a dual network architecture that consists of an expert network that is only trained on online data, and then we have a generalizer that's trained on online data as well as data from a replay buffer. So here we have an uncertainty-based sampling approach that tells us very informative samples that we want to keep to continually train this model nonstop. So here we use a post-graph-based SLAM approach in the back to give us our visual odometry estimates. And we also do loop closure detection on top of this to add them to the post graph. So again, let's see the qualitative results. So our SLAM method is in red, the red line. I hope you can see it. And you can see many other baselines. You also see the baseline here, which is basically just trained on online data. So what you see here is that the SLAM method here in red outperforms even the network that is trained on environment-specific data. This is because there is some useful knowledge from previous environments that the model still can keep that it goes when it goes to new environments, right? So it's not just using new environment data, but also extracting this relevant information from previous environments that it's seen. And this is what that you see here. So here, essentially, a model that's trained on cityscapes, then gone to Kitty. So from some cities in Germany to, again, Karlsruhe, which was Kitty, then robot car, which is Oxford in the UK, and then we now evaluate again in Germany in Karlsruhe. So this tells you that the performance really is not only the same as how you have with online learning, but even better because you have some usable knowledge that you have learned across the way. And we can also do this same strategy for other tasks. For example, here you see here unsupervised depth estimation and panoptic segmentation. Again, using this replay strategy with a replay buffer and uncertainty estimations, we also show here now a model that's trained on Kitty, but online learning right now on cityscapes. So as you can see, both the depth error and the panoptic segmentation accuracy is even better than training directly on cityscapes itself. Again, this shows the ability of the model to leverage knowledge from useful scenarios that it's seen prior to coming to a new environment. And of course, you have depth and panoptic, so you can make these 3D maps that you can use for navigation in the end. All right. Some other maps that robots also need are, for example, okay, let's look at what are the important criteria, I guess, for maps in general. So here you can see one is completeness and accuracy, and to be able to scale to large areas. We want to be able to capture frequent changes in the environment. So these two, I think, you can address using a multi-agent system. And then you have higher level topological information that you might want to capture. For example, what are the street or road directions? And you also want to be able to query the map very fast if you want to do things like, tell me all the street signs in this entire city, right? Imagine a map of the city is very, very large, and you need to be able to have some efficient mechanism for querying. So here we proposed an approach to do this with scene graphs. So collaborative scene graphs, essentially. And scene graphs enable higher order reasoning with very efficient querying for many functions, for robotics, for automated driving. And our proposed approach here used just panoptic LiDAR segmentation of point clouds, the point clouds that I showed you before. And then we obtained this from multiple agents that are driving around in the environment. And we have a collaborative SLAM that detects inter-agent loop closures to build a consistent map of the environment. So what does this look like? So this is what you see here. This is a visualization of a large scene graph environment that we built. So on the lowest level of this pipeline, you have these point cloud maps with each semantic class. That's what you see in the bottom. And then we have these keyframes that we use to build a consistent map of the environment. So these green dots that you see here are essentially the keyframes. And one layer higher than this, other than the keyframes, you have lane directions. So this is specifically for outdoor environments. So the lane directions and the dynamic objects that are moving around. And one layer higher to that, we have landmarks such as street signs or anything else that you might want to query fast. And the topmost, you have neighborhoods or environments. So this is a hierarchical map structure that we built that's very, very fast for querying. And in this initial work, we were the first to do this for outdoor large environments. Lots of people have tackled this in indoor environments before. For example, Lucas Group in MIT. but we also wanted to do this for outdoor, large-scale environments. And very recently, we also extended this approach a month back in an open vocabulary manner. So what this means is that now you don't want to have only a fixed set of categories, but you want this to be open vocabulary, any object vocabulary that you have. So now we can build these scene graphs in the real world that you see here is from the Oxford robot car dataset in an open vocabulary manner for querying any amount of semantic classes. Okay, so thus far we have, I think, primarily looked at two parts of the pipeline: perception, localization, SLAM, map building, and let's get to actions now. So again, let's go back to some inspiration from humans. So if you look at how babies learn, a lot of these cognitive abilities in the first 10 months, or let's say like first 6 months, is essentially by just watching the world around them. So at this stage, babies can't move around, right? So that's why in the video on the top, you see, if you show these very young babies things like objects, like lights and things, they become very surprised because they don't have this, they've never seen this concept before, right? They're like very young, and this excites them like tremendously. But if you do the same after a few months, they're not surprised anymore. They have built this world model of how these toys should look like, how the object should look like, and this is not surprising anymore. And after this period, what they learn is more by physical interaction with the environment. So they do really stupid things like put toys in their mouth, like throw toys, and with this physical interaction, they get not only visual feedback, but proprioceptive feedback, and they build this really strong world models that they use to learn about our world. And we believe that one of the easiest way that we can also teach robots, for example, is to, the same as what parents do to children, essentially demonstrate it. Just show them how to do it, but we don't want like hundreds of demonstrations. We want like one video demonstration. We want robots to teach tasks what is shown in this demonstration. And very recently, last year, we proposed an approach to do this that we call as Ditto. So just in a sec, you see here, so Ditto has very few initial requirements. So we've given a video, an RGBD video of a demonstration, for example, any task, like taking a mug and putting it on another table, for example. So given this video, for each frame that we extract segmentation masks of the hand that is showing the demonstration, the object that the hand is interacting with, as well as the goal object where you want to, let's say, place this object to. And given this set of masks, we perform relative pose estimation in each of the subsequent steps to estimate the correspondence of these objects, how the objects are essentially changing along this trajectory. Then we concatenate all these poses, and we retrieve an object-centric trajectory of how the object moves along the video to reach the goal position. So after we have this, then we have a live scene now where you want the robot to essentially imitate what the human did in the video. So we do the same. In the live video, we have to have the same object, otherwise this doesn't work, okay? So if the same object is there in the demonstration, we again do the same thing where we extract the object mask. We extract a mask of the hand interacting with it. Here it's a gripper, not the hand, as well as the goal place where you want to place it. Again, we now transform this trajectory that we have extracted in the demonstration video, and we warp it to our new scene. And then we use a classical planner to then execute this trajectory that we have in the new scene. And that's that you see here. Again, learned only from one video. So on the top here, you see that things like grasping and putting a Coke can into a tray, for example, a model is able to do this really well. On the bottom, you see that a change in the demonstration. So this works fairly well with objects that look similar, also goal states that are similar. So now we have a tray, but a tray is not in the same place as it was in the demonstration, but slightly lifted. And you can see that this still works quite well at this stage. So other ways that we can also teach robots is by just, again, demonstrating them. And we've done some work in this direction where we have, for example, a reinforcement learning policy where you train on simulation, and then with, again, real-world demonstrations of how a human can show the object, we're able to adapt this model. So what you see here is opening a door. So we're trying to teach the robot how to open a door. We learned this in simulation with Gaussian mixture models. And in the real world, we want to adapt this Gaussian mixture model with reinforcement learning. So that's what we do here. So here we use soft actor critic to then modify the GMM parameters online interacting in the environment. And we showed that only with 30 minutes of real-world interaction, a robot learns essentially how to open the door here. And this bridges essentially one of the problems that you typically have, which is the sim-to-real gap. And another way we can also do this is by just, let's say, interacting with the robot by telling it when it's doing something wrong, right? So humans are going to be there when robots are going to execute tasks. So humans can also tell the robot that, hey, what you're doing is incorrect, right? So here we do interactive learning with human feedback. So while the robot is executing the policy that's, let's say, trained on imitation learning in the real world, the humans around interject and give two types of corrections. One is corrective feedback, where you can, let's say, move the robot to show it how it should actually do. Or you could just say that what it's doing right now is wrong, which is just meaning it's just a binary feedback. So we combine both of these feedback mechanisms to teach these robots, again, even better right now with only 20 minutes of training in the real world. Okay, so what I'm really excited about, I think, is to enable robots beyond performing tasks that are on tabletop settings. Because I think the age of tabletop, there's still many challenges to do that. And I mean, it's great that people are doing it. But I'm more excited about, I think, mobile manipulators that move around in human spaces. So I think the age of having, let's say, even these factory robots, massive factory robots that are fixed on the ground, I think the factories of the future are not going to be like this. I think the factories of the future are going to produce many different types of products. They're not going to be only one product. And for this, the robots need to move around. The environment needs to change more to do this. And we need to tackle this mobile manipulation problem here. So how this is typically done in robotics is you have a controller for navigation for the base. You have a controller for manipulation. And there's very little interaction between these two controllers, right? And if you think about some of the tasks, like, let's say, opening a door, it's very inefficient to first move, then put the handle, and then move back. It's not really efficient when it comes to do this, as opposed to just a straight motion where you can move simultaneously and manipulate objects. And this can be for anything. Just pick and place. Like, you don't have to like move and then pick and then move and then place, but rather you can do this in one motion. How we wanted to tackle this problem is, again, using learning. Here we decompose this mobile manipulation problem into two. So we have an arbitrary end effector planner here shown in green. You can use any existing planner, for example, just A star, if you like. And we introduce now a reinforcement learning agent for the base to ensure that the base movements are kinematically feasible for given the manipulation motions. So the reward function now for the reinforcement learning agent is just the inverse kinematics should be feasible, right? This is really nice because now we have a well-descripted physical constraint reward function, and we can train this on simulation. And we train this across large number of robots in these procedurally generated environments. So here you see 3 different types of robots that are trained in simulation with these random obstacles. You don't need actual descriptions of the environment. Here you see the PR2 robot. That's the Toyota HSR robot. And I forget what's the last one, but maybe Tiago, I think. And we're able to deploy this 0 shot without any training into the real world. So now you see the same policy where Tim and Daniel here are even disrupting the environment, like creating obstacles, and the robot is able to successfully execute the task by autonomously moving to ensure that the manipulation motions are feasible. We do the same again with a different robot, the HSR robot in the bottom. Again, the same policy without any real-world training. We also used this very recently. This is still in review, just a month ago, where we've seen quite a lot of work in teleoperation. I don't know if you've seen all these videos about, for example, just showing robots how to do different stuff with a very inexpensive gripper. But nobody has really tackled this for mobile manipulation, right? How do you show a mobile manipulator demonstrations of how it should do? Because it's really complex. You have to move the base, you have to move the arm. And we thought, why not extend our previous work, which does the autonomous movement of the base by itself, right? This kind of solves the problem. So we just, again, moved the arm. Here, Daniel here is showing the robot he's moving the arm physically of how the robot should learn the tasks. And the base autonomously moves to, again, ensure no collisions and to maintain kinematic feasibility. So we collect a large amounts of demonstration data like this, just showing the robot how to do it. And then we use this to then train an imitation learning policy on top. And this works really well for mobile manipulators. So here you see still the demonstration setting, but later on in these videos, you can see, for example, autonomous execution of this policy from the collected demonstrations. And this enables you now to collect demonstrations quite easily and train any imitation learning policy to achieve this. And we also use this for many other complex tasks. I told you long horizon, right? So we don't want to do, again, one-step tasks, but really long tasks that involve navigation, exploration, articulated object manipulation, grasping, so on and so forth. So what you see here, I think, is a task that we call as multi-object search, where you have an unknown environment that you just put a robot, and the robot has to go find an object that is somewhere in this building, for example, and it has no clue where it is. So it has to, and also the doors are closed, and objects can be, for example, inside drawers or shelves and so on. So robot has to also open things to search for objects. And here we have a hierarchical reinforcement learning policy that essentially composes skills. So it composes exploration, navigation, manipulation, and for each of the low-level skills, you can have any policy as you like an imitation learning policy or a reinforcement learning policy. But now this hierarchical RL policy on top just tells you which actions that you should choose when to have the final, to find the objects. And that's what you saw in this video, basically. And we recently also extended this with language. And what we wanted to do, again, is the same object search task, but we wanted to give an instruction for the robot. So we don't want to use LLMs for getting, interpreting the language instruction, but rather we wanted to use for reasoning. Because the interesting thing in robotics, I think, is we have a lot of common sense priors that are encapsulated in these language models. And we leverage these common sense priors, for example, to know what action to do next. So again, we have a search task here where the text says, like, find me something to eat. And the language model receives this, sees what the objects are in the environment. It has a scene graph that it builds online as it goes, and then navigates to, for example, a kitchen. Then it thinks, for example, kitchen typically has something to eat, right? And then it sees a fridge, and then it says, okay, maybe there is something to do inside the fridge. So this reasoning comes now from the language model at each step. And you can do the same for pure navigation if you want. So here we do pure navigation, no mobile manipulation. Now in an open vocabulary setting, we can give instructions to robot, totally unknown environment, go to this room and find the Christmas tree, for example, right? And this works quite well. This is an office here in Freiburg where we do multi-floor navigation now in an open vocabulary manner. All right, so finally, I want to talk about some of the things that we should, I think, care about that we're not caring about so much. So we've seen as we deploy more and more learning models, especially in robotics, I think it becomes very essential to understand the negative effects or the biases that these models can have. And this is essentially unpredictable, I think, if you are deploying this large scale in the entire world. But maybe if you're aware of some of the biases, we can potentially reduce it. I don't know if you remember, I think 2 years back, there was this Uber car crash that it didn't find a pedestrian on the street. This was essentially because the training data was not descriptive enough to find certain people. Or the Microsoft chatbot Tate, I don't know if you remember, again, a few years back, as soon as they released the chatbot, it started acting not how it's supposed to do. It was very rude, and they took it down very fast. So these unpredictable biases that you might introduce into the learning algorithms, I think in robotics they have a far adverse consequence as some other fields that you might have. And for this, we collaborated with ethicists, lawyers, social scientists, roboticists to create this very large survey that we extrapolated to robotics. How can we address potentially some of these biases that you have? You might also hear this with tomorrow's keynote, but this is just an introduction to this topic as well. So with that, I'd like to thank you for your attention. I'd like to thank my students as well as the funding agencies that you see here who made all of this work possible. Thanks a lot for having me again. I'm happy to answer questions that you have.
So thank you, Abhinav, for your inspiring talk. So now we are open for questions. Any questions? Questions?
Hello. Thank you, Abhinav, for your inspiring presentation. My question would be like more philosophical, I would say, or target aiming for our research. Do you think it's like more about the data set or how we handle uncertainty today? We need to improve our robots to understand how the observation should be received in the system, or should augment our data sets?
I think it's both, right? Because you still need data to learn, but I think what is important probably is the right data. So this is where I think structured learning, right? You want random data, but you want right data. So also how to obtain right data or how to choose the right data from a lot of noisy data is still an open problem. Yeah. We can't just use random YouTube videos to teach robot all kinds of stuff. So yeah, we would definitely still need data, but right data is a big problem.
I see. And what is your opinion also about synthetic data today?
Sorry, what was the question again?
Synthetic data today, the generation of data through like algorithms and so on.
I don't get it. Wait, once again.
Yeah, what do you think about generating synthetic data?
So I mean, that's a good question. So I think simulations are only going to get better and better, right? Like NVIDIA is doing a great job pouring tons of money into this, and simulations are going to be better, but you still need to do, I think, some level of sim-to-real transfer because simulations still can't capture the real-world physics that well, right? I mean, we can, I think, now do pretty good simulations, but sim-to-real gap, again, is the bottleneck there. And I think what's going to work really well in the future, we started working on this a few months back, is combine simulation, combine various forms of data that you have, right? Little bit of internet videos, a lot of simulation, some demonstrations, and some corrections. I think that's like, if you have a nice approach that puts all of this together, so that would be, I think, the best that we could do in the immediate future.
Yeah, thank you.
More questions? If someone would like to do the question in Portuguese, I can try to translate for Abhinav also.
Okay, thank you very much for a wonderful presentation. Very nice work. I have two questions. The first one concerning the hierarchical arrangement that you have, where you have all those green points, and then we go down to the lower level in the collaborative.
Yeah,
so my question is concerning latency. In the communication among your agents, how does that impact the whole scenario? That's the first question.
Yeah, great question. We never touched that part. So we assume that people who do the reliable communication efficient multi-agent would tackle it. So here we only focused on essentially just building multi-agent SLAM, but we didn't really pay so much attention to latency or memory efficiency and things like that.
Okay, great. There's so much we can tackle at once, right?
Yeah.
Okay, the second question is concerning the learning approach with your mobile manipulator, okay? Do you use the haptic information or just position?
In this position and force feedback. So we don't use haptics or proprioceptive or touch. It's something I'm working on right now, combining touch feedback with vision to collect demonstrations, for example, but not so far.
Okay, thank you so much.
More questions? Any questions? Oh.
Hello, so thank you for the presentation. And I've read the Correct Me If I'm Wrong paper as soon as it was published, but over the years I've not seen you guys in the lab publishing any more interactive learning methods. And I would like to know if is there a reason, because I think it would work greatly with the online continuous learning methods, because I think it's kind of how the humans work. We learn a lot on ourselves, but a lot with examples over the years.
Great question. I think the answer is that just because the PhD student was more excited about new things that was coming after, no other reason. Because there's so much happening, right? Like, I think people get excited with new things that are coming up, and was nothing specific, I think. But actually, 4 days ago, I think, we put up another paper, which is, again, interactive learning, but different form. So what we tried to do there, I forget the name of the paper, but it's there in the lab page, the first paper now in the publications, where what we tried to do is we tried to tackle ambiguity. Again, everybody wants to work with language now, right? So it's, again, interactive learning with language, but let's say that there's an instruction that you give a robot, like, get me a soda. But now the robot goes and finds that there are many types of soda. What should it do, right? It's a very open-ended question. So we tried to, for example, help the model reason better with interactions that a human can give with language, again, while the policy is executing when you have ambiguities. So I think that's still interactive learning with a modern LLM twist. Yeah, to answer your question again, no other reason that than what the PhD student was interested in.
More questions? So our time is finishing, but I have the last question, Abhinav. One thing that you mentioned, and that is, so in some way the world is partially observable. That's the word. The word is, I don't know what's behind that door. It's impossible to know. And the humans dealing with that in some way, right? One thing for me is uncertainty. Humans knows that there are things that you know and things that you don't know, and some way humans and animals, you can generalize for animals. But you mentioned that the difficult for the models, the learning models, to dealing with this world, unpredictable world. And humans and animals do a thing that long time ago researchers look for, that's active perception. Means instead of to have a passive perception, just have videos that came from everywhere, I don't know, the robots can move to see better, to understand better the world. Do you think active perception is the next barrier to try to approximate the capability of babies in terms of perception to the robot? Do you think?
Definitely, I think active perception is a big ongoing challenge. And I think it fits well with everything else here, right? So for example, if you looked at the continual learning part, okay, there's no actual planning, but now if you combine this continual learning with the other RL policy that does it, which actually does planning, so you can have, one of the low-level policies is like if you have, actually we're thinking of a master student to do this, but it didn't work out. But one of the low-level policies, if you have very low uncertainty, then one of the things that the high-level policy can do is go do active exploration to get more data to do better things. So I think it fits quite well in my head in the whole framework. And definitely you can never capture the world, right? That's the essence of the talk. And here, active learning will play really a big role in online improvement of the model further.
So thank you, Abhinav, and thank you, everyone. So we are closing this session, and let's go to the next.
Thanks a lot once again.
So now we have lunch until 1 p.m. And after you have returned here for more sessions, yes, in the rooms. Thank you, guys.